Hello and welcome to Unit 3 in Integrated 3. We're going to be looking at what will eventually become a cubic polynomial. And we're going to do this by looking at a story that began in Integrated 1 about somebody named Scott who's going to do some push-ups. He's going to do them for charity, and he keeps track of how many he does. So when this problem was given in Integrated 1, the students were expected to find the explicit equation and the recursive equation. So remember, recursive means building on what you had before. It's a lot like dominoes. One domino knocks down the next one. So if you start with 3, as you can see in figure number 1, then the next day he's going to add 2 more, then 2 more on top of that, and then 2 more on top of that. So in a recursive equation, you're going to start with, okay, where is the beginning? The beginning, the a sub 1 was at 3, because there were 3 push-ups. And then to get any push-up, that would be a sub n, you take the previous number of push-ups, that's a sub n minus 1, and you're going to add 2. That's the recursive equation. Now, we also learned in Integrated 1 that you can create an explicit equation. Explicit means you have the ability to jump anywhere in the pattern you want to. It's a lot like a vinyl record or a CD player or CD. So for this one, a sub n comes from, where does it start? It starts at 3. And then because we're using day 1 and not day 0 as our beginning, we're going to put in an n minus 1 and then the common difference. And that was 2, because we're going up by 2. We'll simplify this a little bit by doing the distributive property. 3 plus 2n minus 2, and that becomes 2n plus 1. So you can see in the diagram where the plus 2 comes from. It comes from adding each time. But where does the 2n plus 1 appear in the diagram? Well, here's the extra 1 at the end, and here's a group of 2. How many groups of 2? 1 group of 2. On the next diagram, 1, 2 groups of 2. Then 1, 2, 3 groups of 2. Finally, 1, 2, 3, 4 groups of 2. And each of them has that extra plus 1 at the end. So this is a review of what we did in Integrated 1. Now let's go to Integrated 3. So now we're going to look at the total number of push-ups that he does in a day. So for example, this number 8 comes from adding 3 plus 5 together, and it will give you 8. 8 added to 7 is going to give you 15, and so on and so on. So what you should be able to do as you go across, you can see day 1 inside of day 2. It's even there inside of day 3, and it's there inside of day 4, because you're accumulating it. You're adding it as a total. And you can see day 2's contribution. That would be right here. That's the new push-ups. But there it is again in day 3, and there it is again in day 4. And so on and so on. Okay, so each day contains the previous days inside of it. So write the recursive, write the recursive equation for that. Well, now you're adding increasingly large numbers. But remember, the pattern for that is 2n plus 1. So the recursion starts, and we're going to use function names for this. G of n is g of n minus 1, so that means the previous day's number of push-ups, total number of push-ups, plus 2n plus 1. That means the added on number of push-ups for that day. Now, let's test it. Okay, let's take a line of this formula, like 5. So that means that g of 5 should be the amount that you had the day before, and that's 24, plus 2 times 5 plus 1. So that's 24 plus 10 plus 1. Guess what that is? It's 35. It's this number right here. So that formula works. It's generating for us the next total amount of push-ups. Okay, now we're going to do the explicit. And the explicit is a little bit trickier, but here's something that we can notice. If we take any of these days and we rotate it 90 degrees to the left, in fact, not 90, 180 degrees to the left, so this way, we can actually fit a copy on top of a copy. So let me show you what that would look like for day 3, for example. So let's turn on, let's see, let's do a grid paper style. We'll come over here. And so first I'll make a copy. So we're going to start with 3. Then we're going to have 5, because we added 2 more. And then we'll have 7. Okay, now I'm going to take a copy of that and rotate it and place it on top. So that means this first row of 1, 2, 3 is now going to be up here as 1, 2, 3. Then this 1, 2, 3, 4, 5 is going to be right here, 1, 2, 3, 4, 5, right next to it. And then the last one, we had 7, 1, 2, 3, 4, 5, 6, 7, will go over on the left, 1, 2, 3, 4, 5, 6, 7, right here. Now, why is that special? Well, because this makes a rectangle, and that rectangle is double the total. Double because there's 2 of them. So let's think about this first in numbers. So you have 3, and then you have a group of 2, a group of 2, a group of 2. So you have 3 groups of 2 plus this extra one, and then you have these extra 3 now on top. Now remember, for a rectangle, the area is the length times the width. Now here's what we're going to do. We're going to change 3 to n. So let me change color here. We're going to go n. We're going to change this to n. Okay. And if we multiply together, n times 2n plus 1 plus 3, that product, that multiplication, is twice as big as it should be. So we're going to cut it in half. All right, now simplify. N times 2n plus 4 and divided by 2. Now, as far as reducing goes, if you have a product that gets divided by another number, you have to choose which of the 2 factors you're going to divide into. So let me give you a quick example to the side. Let's say you're going to go 4 times 6 divided by 2. Well, you can say, okay, 2 goes into 2 once, 2 goes into 4 twice. Then you have to do 2 times 6 is 12. What you can't do is divide the 2 into both factors. So you can't then go, okay, 2 goes into 6 3 times. That way you would get an answer of 6. That is totally wrong. So don't do that. Back to our problem over here. I don't really want to divide 2 into n, but I want to divide 2 into the factor 2n plus 4. It's going to have to get divided into both those terms. So 2 goes into 2 once, 2 goes into 2 once, 2 goes into 4 twice. Now what do I get out of all that? N times n plus 2. That's the formula for the explicit. So coming over here, and that would be called, well, I guess it would still be called g of n. So g of n is n times n plus 2. Let's see if it works. Again, let's do g of 5. G of 5 is 5 times 5 plus 2. That's 5 times 7. That's 35. Bingo. There it is. That 35 again. So this formula works. All right. So now that we've developed that idea, now Scott's going to do something crazy here. Look at this table. Scott's now going to take the total number of push-ups he completed for the month last year and do that many push-ups each day. So we got to build out this table. Okay, so it's still going to start with 3. But now we're going to add 3 and 8 together and get 11. 11 and 15 together and get 24. Okay, so you notice that g of n and m of n are the same numbers. So this is still 24. If we could extend the f of n to 11, this was 35. 35. 24 and 24 would be 48. And then the last one on that, for the table anyways, 85. So remember, the first column, f of n, was 2n plus 1. Okay, the next two columns are the same. They're n times n plus 2. This last column, and we're going to do it recursively, t of n for total. T of n is the previous entry, t of n minus 1, plus the formula for the previous column, n times n plus 2. So, number 3, how many total push-ups on day 4? 48. No, I'm sorry, not 48. That would be, I made a little mistake back here. Hold on. That would, 11 and 15 is 26. This is 26. This is 50. 85 is still right. Okay, so this is 50. And we did number 4. That's here. Oops, I erased it. That's here. This is number 4. And then number 5 says, without finding the explicit equation, make a conjecture as to the type of function that would represent the explicit equation for the total number of push-ups Scott would complete on a given day. So type of equation. Well, let's go through them one by one, and I think you'll see the pattern right away. So this first pattern here, this is, this formula is linear, but it comes from a constant change. This formula is quadratic, and it comes from a linear change. Okay, quadratic means like x to the second power is the highest power. And linear, well, they're using n, so we'll just say n to the second power. You're going to get that if you distribute this. This would be n is the highest power. So that last one over here, that's going to give you n to the third power. So this is n to the third. It's also called the cubic function. How does the rate of change for this function compare to the rates of change for the function in the jump start and the problem number 1? Its rate of change is quadratic. That's what that n times n plus 2 is. That's actually n squared plus 2n. That is totally quadratic. Test your conjecture. This is number 7. Test your conjecture from problem 5 and justify that it will always be true. See if you can move to a generalization. So you can do this, for example, by looking at differences between the numbers. 3, 11, 26, 50, 85. 3, 11, 26, 50, 85. And you say, okay, how far from 3 to 11? That would be 8. How far from 11 to 26? That's 15. How far from 26 to 50? That's 24. From 50 to 85, that's 35. Those numbers should look familiar because they're in our table. Then look at the difference of those numbers. So 8 to 15 is 7. 15 to 24 is 9. 24 to 35 is 11. And those numbers should seem familiar because they also were in our table. Now, lastly, look at the difference again. 2 and 2. Now, count how many levels we had to go to get there. Level 1 differences, level 2 differences, level 3 differences. When the third level difference is constant, you have a cubic. So third level difference is constant. Now, ready for more? It's kind of interesting. Come up with the explicit equation. There is an easy way to do that on Desmos. So ask your teacher if you want to know how to do that. Let's do the takeaways real quick here in the box. Okay, so rate of change of a linear function is going to be a constant. The equation is, in words, next equals previous plus some constant. It's the same constant of the rate of change. The equation, y equals mx plus b, quadratic. This has a linear rate of change, not constant. It's constant second difference. That would be next equals previous plus linear. That equation would be, and you might remember this from integrated 2, finally, a cubic function will have a quadratic, oops, let's spell it correctly, quadratic rate of change. So that would be a constant third difference. So our next equals previous plus quadratic. And that would look like, if we use all the letters of the alphabet, ax cubed plus bx squared plus cx plus d. Cubic function. All right, so very good. The lesson summary, take a look at it. We did some modeling with quadratic and cubics. This is the table you want to pay attention to. We'll see you next time.